A magic square is a grid of numbers where all the sums of rows, columns, and diagonals are equal. A magic square of squares is also such a grid, but all the numbers are perfect squares. No non-trivial solution has ever been found. This is my third and final video on the subject, each one getting closer to a resolution than the last. I personally believe there are no solutions possible, I just do not have the ability to prove it. What I'm here to show instead is how you can get arbitrarily close to such a solution, and I will share my almost magic square of squares that I generated, and how you can make one too. No prior knowledge of my other videos are needed. Let's begin. We can write down the 8 expressions needed that must all be equal to solve the problem. 4 of the equations have a common term, that's the center cell, and can all be grouped together. Substitutions can be made to reduce the 9-variable problem into a 4-variable one. It can be further reduced to a 3-variable problem by equating the first row and diagonal together. The 4 expressions all equal the same value, which we can now find using the reduced 3-variable grid. It turns out they all equal 2e squared. We need to bring back the 4 relations we discarded earlier, but we can find new ones matching the form of the ones we already obtained. Notice how the D cell has just 2 terms and can be rearranged to match the form of the other 4 equations. Due to symmetries of the grid, we can find the remaining 3 relations by rotating the selected cells. We now have our 8 transformed relations that must be satisfied to solve the problem. We must now find a way to easily generate solutions for our constructed form. This looks very close to the Pythagorean theorem, and it is already well known how to construct Pythagorean triples. If we multiply both sides by 2 and perform substitutions, we get very close to an answer. We just need the left side of the equation to be split into 2 perfect square sums. It may feel arbitrary here, but if we split it evenly and add certain terms to one of the expressions and subtract the same terms to the other expression to keep the whole thing balanced, these 2 expressions can now be factored. This gives us a way to always generate a solution by supplying integers into m and n. Now, the naive approach would be to try and solve each of the 8 equations individually. We can be much more efficient by solving these 4 solutions simultaneously with the help of an identity. This identity lets us solve for 2 pairs of some squares, but we need 4 pairs. So let's add 4 more variables. This lets us apply the identity twice to end up with 4 massive equations all equal to each other. Now we have 8 of the 9 variables filled out. We're not done here yet, because all 4 of the expressions generated are meant to equal 2e squared, and it's not guaranteed that whatever r variables we put in will give us double a perfect square. This requires an additional set of constraints. As far as I'm aware, these are all of the unique ways you can set up constraints for the r variables, such that you'll guarantee double a perfect square if they're true. Out of these 8 sets, only a few are solvable with our current knowledge. From here, I picked the 3rd remaining set of equations, as I can apply that special identity once again to the last equation. Solving the 8 r variables gives a new set, which I will call the s variables. So finally, plugging in any values for these will always give a solution for the 4 pairs of square sum solutions, and they will all equal double a perfect square. But remember that we still have 4 other equalities to fulfill, and trying to solve just one of them means dealing with a most monstrous Diophantine equation that I can't even put on this video because of how many terms there are. It's at this point where analytical approaches will no longer be useful. That means it's time to think graphically. Here I have plotted the 4 remaining equations, which you can see written at the top left in the highest block. Underneath are each of the corresponding 4 equations plotted on the graph to the right, color-coded. Since this is an 8-variable equation, I had to fix 6 of the variables so that the remaining 2 can be used as free variables x and y, so that you could see the graph on here. Now, every point on one of these lines is a solution to one of the 4 remaining equations. And you may notice something, that there are only 2 colors here. And one of the shocking facts is that is because the equations are sitting on top of each other. If I disable the green line the red line shows right underneath it. And if I disable the black line, the blue line shows right underneath it. So despite the red and green equations not equaling to each other analytically, and the black and blue equations not equaling to each other analytically, they seem to be sitting on top of each other regardless. It's too cumbersome to analyze the reason for this, but I suspect that there are other asymptotes that exist in one graph that don't in another, and are thus unequal at specific values. Regardless, for our purposes, we can treat 2 of the 4 equations as redundant. This leaves us with only needing to find points where the black and green lines intersect, as this will basically mean all 4 equations are satisfied at this point. As you can imagine, fiddling with the s variables and searching for integer-only solutions is a futile task, and at the minimum requires the points you're inspecting to be rational for both x and y. Good luck finding an exact expression of these numerical points using any type of solver. Remember, we are working with a 16-degree polynomial equation. Quintics are where the Abel-Ruffini theorem start to kick in, where it's not guaranteed to find algebraic solutions anymore. And that is 11 degrees further down than where we are currently. If we allow ourselves to resign on the possibility of finding purely integer solutions, the next best thing we can do is to get as close as possible to 1. For some s variables that you assign to x and y on the graph, there may be 2 other s variables that, when changed, only cause a linear change in the intersections along the x and y direction. For example, watch this intersection as I manipulate S4. Changing S4 causes a steady change in the position of the intersection only horizontally. Now watch the intersection as I manipulate S6. Changing S6 causes a steady change in the position of the intersection only vertically. And we can determine what the rate of change for either of the directions are by taking the difference of 2 S4s for the x direction and 2 S6s for the y direction. And since setting either S4 or S6 to 0 causes a full collapse of the solution space, this means there's no offset value to worry about to capture in some sort of formula. We just need to care about the slope. We can then use this slope formula and multiply it by a bunch of different constants to find the product that gets the closest to an integer. For the x direction, our input is S4 and the product becomes the S3 solution. For the y direction, our input is S6 and the product becomes the S5 solution. For example, these are the 4 s values I'm making to be constant. And these can be any value as long as they're not 0 or equal to each other. And after shifting S4 around, I found this resulting slope and thus have this equation. I then wrote a program to try every S4 from 1 to 1 million and picked which of the S4 values resulted in the closest the product gets to an integer. The actual reported S3 value is just a bit lower than that, with 7 nines in the decimal place. That's how close it is. Now we can do the same trick, but for S6 and S5, and after that, we have, at last, our first ever candidate to challenge the magic square of squares problem. Now we must work backwards by using the s variables to solve the r variables, and then use the r variables to solve for a, b, c, d, f, g, h, and I. E is solved in the process. And remember, this exactly solves 4 out of the 8 equations we have, but nearly solves it for the other 4. These values, when finally squared, reach over 70 digits long. So how close is this to a solution? Checking one of the remaining 4 equations, we can see a lot of the first digits match from both sides of the equation. And if you take the ratio between the two, it's nearly 1. Now if you have a lot of extra time and compute power, you can find your own better magic square of squares by following the steps I took. As for me, I've gone farther than anybody else has on this problem, and then went even further. I have nothing left to prove here, and I'm freeing myself from this diabolical problem once and for all.